company is the brainchild of our founder, Andy Winter, who started this company in Cambridge at 2002, which is almost 20 years from now. And there was a promise behind this software. It was to use a newly designed force field, which is called the Extended Electron Distribution Force Field, or the Z force field. And the idea behind this was to introduce a force field which is very different from the traditional ones. The traditional force field, which we generally use nowadays, tends to put charges mostly on the atom center. They generally perform well, but due to this more simplistic definition of charges, the more subtle interaction cannot be actually accurately modeled using this force field. And here Z force field is illustrated the sigma and the pi charge. The sigma charge goes on the atom center, and the pi charge goes on the pseudo Z atom. And the separation of this sigma and pi charge actually allowed an excellent modeling of several effects, such as polarization effect, substituent effect, atomic charge anisotropy, or aromatic aromatic interactions. And this is a high quality molecular mechanics force field with an excellent coverage for organic molecules, water, and proteins. Now, to illustrate the power of this Z force field in getting detailed ligand interaction pattern, we can explore how the electron density changes as we go from toluene to which has been substituted with halogen down the series. So here you can see this red electrostatic cloud is positive in nature, and this blue electrostatic cloud, which comes from for this pi electrons over here in toluene. When we substitute this with fluorine, we can see that the pi density is being pulled out of the ring because this is more electronegative in nature. It pulls the pi density out of the ring. However, with chlorotoluene, which is also slightly electronegative in nature, but it has a difference with the fluorotoluene because in chlorine, it donates back the electron to the ring. So here you can see there is a change in the electrostatics surface, and you can see here there is a thinning of the negative electrostatic cloud and formation of a sigma hole here. So this makes the difference when we calculate it with the Z force field, and it helps you to differentiate between compounds based on the electrostatics. In the similar way, it also helps you to understand the electron density change for aromatic compound. This is sildenafil, which is a known drug molecule, and these are its analog. You can see here, though the 2D structure doesn't vary much with this analog, but there is a huge change which has happened in its electrostatics. And the vardenafil, which is almost similar in terms of electrostatics to the sildenafil, is actually the second most potent compound in the series after sildenafil. And hence, in the Z force field, this complex description of charges result in more detailed understanding of the aromatics as well, which ranges in a wide, which has a widely spread in the drug discovery area. So understanding the electrostatics of aromatics is very important in drug discovery. Now, comparing molecules using this full electrostatic surface would be actually comparing molecules using this electrostatic surface. So here you can see sorry, I lost my connection. Hello, am I audible?
Yes, yes, you are out.
Yes, sorry, I lost my connection. Uh, just just give me a minute. I'm resharing.
Okay.
I hope my screen is visible now.
Yes.
Okay, thank you. Um, so as I was saying that comparing molecule using the full electrostatic potential would be computationally very expensive. And here Crescent came up with the idea of a new concept, which is called fill points. These fill points are points that are placed at the local field extrema, the areas where the fields are at a maximum value. So these fill points are placed at a region where the fields are at the maximum value, and these fill points are used as a cut down representation of the full potential. The blue full points here corresponds to the negative electrostatic surface. The red fill points corresponds to the positive electrostatic surface. The yellow fill points here corresponds to the electrostatically neutral surface, which gives a shape descriptor. And the orange fill point here corresponds to the hydrophobic surface. So this fill point is a concept which is spread over all the Crescent softwares, and they have used this fill point for various purposes such as aligning molecule, comparing between molecules, and also calculating the electrostatic complementarity. The other function that you can calculate is the electrostatic potential surface, both on the protein as well as the ligand. So this is very commonly done within drug discovery to understand the complementarity or what needs to be changed in terms of electrostatics so that your ligand gets a better match in the active site. So you can either visualize this on the protein and ligand and then do it in a very traditional way of comparing. But what the Crescent software has done is they have introduced a concept called electrostatic complementarity. So what it does is analytically does the comparison for you, and then it produces a surface which is called the electrostatic complementarity surface, and then it produces a surface which you can visualize either on the protein or in the ligand. And then you can then decide on which part of the molecule electrostatics has to be changed to make it a better match. By default, we colored the match as green and the clash as red and white as neutral, which is not either not match or clash, somewhere in between. So here you can see that this biotin stretavine complex of protein and ligand. This is a very good complex where the ligand is very much complementary and quite active. But you can see here there are small patches of red here and here, which which if you can change the functional group, it will be able to make a better match and which will have a better activity. You can also generate a score out of this electrostatic complementarity, which you can then use as a subsequent method post docking. And in cases where you can validate a good correlation between the score and the experimental activity, if you have any from your labs or maybe from literature, then you can use this to predict the intrinsic activity for your design compound. So this is a very good functionality where you can make changes in the ligand looking at the surface and looking at the clashes, and then you can regenerate the EC score to see that if the EC scoring has improved in your new design. So this is a very good way how you can improve the activity for your ligand. So this is all about the unique science behind the Crescent software. Now I would start speaking about each of the modules that Crescent software have. But before that, I would like to ask that if you have any question from this part. Do you have any question from this part or should I go ahead?
Okay, you can go ahead.
Okay, thank you. So one of the major module in Flare is docking. The docking and scoring in Flare is performed using the Lint Finder docking algorithm. The lead finder docking algorithm generate docked ligand poses starting from a 3D structure of the protein, which you might either get from the X-ray crystal structure, or if you do not have a crystal structure, it might be modeled using a homology modeling tool as well. And you need to have one or more 3D ligand structures. Now, lead finder assumes that the protein is rigid and then analyze the possible conformations of the ligand by rotating the functional group along each rotatable bond and then generate the best poses out of it. So there are three different scoring functions in the docking. One is the LF rank score, which energy ranks the poses. So it gives the lowest energy to the pose which has the lowest binding energy, and this is used not for differentiating between the binding energy, but this is for only the rank ordering the poses. So it gives the best score to the best pose. Then we have the LFDG score, which is the binding energy prediction. And this LFDG score you can use for differentiating between which is a better binder, mostly in a congenetic series of ligand. And then you have LFVS score, which is the virtual screening score. See, if you are carrying out a virtual screening using docking, then you can use this LFVS score for differentiating between the actives and the inactives. We have different flavors of docking, which I will explain on the go. Uh, we have template docking that is used when you have an extra crystal structure and you want to use that template pose to seed your docking run. So in a congeneric series of ligand, this template docking can be used where the extracrystal structure is defined as the template. And then you can run a docking calculation, which will align the rest of the ligand in the series with that template and try to generate poses which are more aligned and more similar to that of the extracrystal structure. And then we have ensemble docking. So ensemble docking is almost similar to that of a flexible docking. But what here is done is considering that the active site is flexible, when you have some difference, some alternative active site conformation for the same protein available as a crystal structure, or the input can come also from a molecular dynamics run where the side chains have different conformations. So you can include all the protein structures that are present with different conformations, and then you can run the docking. So what the docking module for ensemble docking does, it it generates the base poses across all protein conformers that are saved, and they save them in the docking results. So here you can see that it keeps the binding energy with each of the protein conformer that you have added here. These are all same protein, but there is some change in conformation in the active site. So you would understand that where the binding energy is best with which conformer, and then you can choose that conformer for binding of the ligand. So this is a kind of docking which is almost, it gives similar result to flexible docking. And then you have covalent docking. So this covalent docking is a module in FLAIR to predict the binding pose and interaction of covalent inhibitors. So if you have a covalent ligand which have all of these electrophilic warheads, then you can use the covalent docking. And in this case, the FLAIR automatically recognizes the multiple nucleophiles that are present in the residues. And while carrying out the docking calculation, it produces this pseudo covalent bond and then gives you the energetics for the covalent docking. So this is a very useful module when you carry out a covalent docking. So when you have covalent warheads present within your ligand, you might be using this particular module for running your docking calculation rather than the normal one. So already in the manual, you can see that these are the warheads that are defined. If you have some warhead which is not already defined, and you can reach and write to the support, would customize that warhead for you so that you can run your covalent docking calculations. FLAIR also has a very unique functionality which is called flickering water for docking. So in some cases, there is a bridging water molecule between the ligand and the protein residues. And this bridging water molecules contributes to the ligand. What you can do is you can mark this as flickering water and then include this water in the docking. What this model will do, it will switch on the water and calculate the binding energy, and it will also switch off the water and calculate the binding energy. So it will help you to understand that how important this water molecule is in binding of this particular ligand. So this is a very, very unique functionality and important functionality in Flare, which you can use when there is a bridging water present. Now, if there is some torsion angles which you want to keep fixed while running the docking, or if there is any core in the ligand which you want to freeze while running the docking, because that is very much important information that you want to not disturb while doing the docking, you can put it a constraint while running the calculation. So that option is also present within Flare. Um, After docking, a very important functionality has come up in the recent version of Flare, which is MMGBSA. So MMGBSA is molecular mechanics general bond surface area. It is a method to calculate the ligand protein binding free energy. So the MMGBSA binding free energy is derived mostly from molecular dynamics, molecular mechanics, and it offers a advantage of being more theoretically rigorous compared to the empirical scoring function that you generally use in docking, and it benefits the and it has a benefit that it is far less computationally less expensive than the relative binding free energy, which we call FEP. So it is much less expensive than the Flare FEP, but it gives a much reliable and theoretically rigorous method compared to docking. So what you can do is you can generate a MMGBSA scoring after running on your docked poses after you have run the docking, and then you can try to correlate it with any experimental binding energy which you have, and try to see that how good it is giving the scoring. If you find that for a series of ligand, if you have a benchmarked amount of data for known binding energy, you can benchmark that data, and it will help you to understand that MMGBSA is giving you a better binding energy, and you can use this MMGBSA scoring for predicting the activity for or the binding energy for the rest of the ligands. You can either run it in an implicit solvent model, or you can run it in vacuum as well. There are several solvent models that are present. And you can also choose to minimize the protein and ligand using this MMGBSA force field, or you can either not also choose to minimize it. So it uses two force field, either open effect or amber gap and gap free force field for small molecules. So you can choose between this force field while running the MMGBSA calculation. So this is the produced data in-house. So this has been taken from this paper which has the experimental binding energy, which has been plotted along the x-axis. And this is the MMGBSA calculated energy using the Flare software. And you can see here the R-square value are quite good, which means that there is a good correlation between the experimental delta value and the calculated delta value with MMGBSA. So you can try that for your own in-house data or any literature data to run a benchmark experiment and see that how good MMGBSA is predicting. Let me now speak about the ligand-based method which Flare has. So Flare has an advanced ligand-based alignment method, and this is based on the Z force field and the fill point, as I said. So this helps you to align a series of ligand with any reference ligand, which might be a X-ray crystal structure ligand, or it might come from pharmacophore modeling as well. So it depends on what kind of data you have. But using this conformation hunt and align module, you can generate a number of conformer for your ligand, and it will then align the lowest energy conformer with the reference ligand, and accordingly you would get a several aligned ligand. And this functionality is actually very important before you calculate your electrostatic complementary score. So for electrostatic complementary score, if you have a generic series of ligand where the functionality does not vary, you can only align those ligand with the reference X-ray crystal structure ligand and then run a EC scoring so that you can get the score for it. And this is a very important module to run before you run your QSAR experiment. So before running any QSAR module, either qualitative or quantitative, you need to run the alignment. So this is a very important module for that. And while doing the alignment, you can also include the protein structure or the target structure. And then while running the alignment, you will consider the excluded volume so that if on any alignment it clashes with any of the residue of the protein, it will put some penalty in the scoring so that it takes care that the alignment remains perfect. Torsion analysis tool, which is based on the every event. So here the torsion angle are colored based on the traffic light coloring. So the red means it's low frequency. This is based on the CST database, the Cambridge Structural Database. So the red means that this kind of torsion angle is generally not seen in drug molecules. And the yellow means that this is sometimes seen in drug molecules, and the green means that this is highly probable in drug molecules. So once you have your ligand structure and you have done a conformation hunt for it, then you can run this torsion analysis to check that if all of its torsion angle lies in either the yellow or the green region. And if you see that some of it lies in the red region, and if you want to turn it to green, so there is a editing tool where you can just rotate the torsion angle, and it will show you a plot like this where you can bring it from the red region to the green region. So it's pretty easy to edit the torsion angle and bring it to a region which lies in the green and mostly found in drug molecules. So this will help you to get a better conformer for a particular ligand. While after docking or maybe in extracrystal structure, you can use this ligand interaction tool, the contact map tool, where you can look at all the interactions that a ligand pi interaction, hydrogen pi interaction, hydrophobic interaction, or any steric clashes that the ligand is having with the protein. So you can look at it in a 3D perspective. We also have an option of visualizing it in a 2D format, which is highly interactive as well. And then you can save that 2D picture in a 3D format as a PDF file, or also copy that and paste it in some presentation for putting it in a publication. Here you can see that these two ligands have the pi equal value of 10.3 and one has a slightly lower pi equal value of 9. But if you look at the ligand interaction, both of them are forming the same ligand interaction, that is a hydrogen bonding and a pi hydrogen interaction. So from here you will not be able to understand that this interaction is probably giving a higher activity for this ligand and a lower activity for this ligand. And here the electrostatic surface comes into the picture. So here you can see here the electrostatics has been plotted on the ligand surface, and near to this oxygen, which is electronegative in nature, the oxygen, this has a negative electrostatic surface which is blue in color, whereas close to this tetrazole, which has a CH pair, this is slightly less negative and slightly reddish and whitish in color. In fact, the same electrostatic surface on the protein. So here you can see the protein has a positive electrostatic surface for both because the protein is the same protein. So for matching with this positive electrostatic surface, it will favor to have a negative fluid pair. Now look at the electrostatic complementarity surface. So here you can see that the electrostatic complementary surface is completely blue, which means a perfect match. But you can see a slightly red and white patch here, which means this is a clash. And if you look at the EC score, so this score is higher than this score. So this somehow explains that why the activity of this particular ligand is more compared to this ligand. So this is just a small example. When I send you the training material, you will get to see that we have done this for a series of ligands, and then explain that how easily you you can differentiate between them based on this electrostatic surface and score, and then that will help you to design a new ligand which has a better activity compared to the original one. Um, I would now look at the other important ligand-based method that we have. We have a QSAR module which has both qualitative and quantitative SAR. The qualitative SAR has two modules. One is activity address and the other is activity minor. What activity address does is summarizes the structure to relation landscape into a informative 3D map. So it helps you to understand that which part of the molecule have got electrostatics or is it hydrophobic in nature and how much it contributes to the activity of the ligand. We also have an activity minor module which helps you understanding the structure to relation in more detail. So here you can see a ligand in the middle and there are about 10 ligands around. The red block here means that this ligand is less active compared to this particular ligand, and the small violet patches here shows that which part of this ligand differentiates from the middle ligand. So this will help you to understand using this activity minor module. It will help you to understand which part of the molecule, which particular part of the molecule or which structure of the molecule is contributing to the lowering of the activity or increasing of the activity. So it helps you understand in more detail the structure active relation. So another module which you have is quantitative SAR, and the quantitative SAR has a field user model which is based on the Z force field, which does a prediction based on quantitative SAR prediction as well, and also gives you an interpretation where you can correlate the results with the surface as well. But it also has a robust machine learning method for regression and classification. So these are the machine learning methods that are included within the quantitative SAR module, which help you to build a very vigorous model for QSAR. And then once you have built a good model for QSAR, you can use that model for predicting the activity of molecules, and that will help you to design better molecules for your in-house synthesis. QSAR model can also be used to model the ADME properties as well. It has the capability of running both 3D and 2D QSAR. So if you want to run a 3D QSAR, it considers the electrostatics and the volume of the molecule. But if you want to run a 2D QSAR for 2D molecules where you do not have 3D structure and you want to run a 2D QSAR, you can either use descriptors which are calculated something like molecular weight, SLOP-P or TPSA, or you can also bring in the set of descriptors from RDKit. So now FLAIR has the capability of bringing descriptors from RDKit as well. So you can download those descriptors and use that for building your 2D QSAR module. FLAIR has a very user-friendly module for QM calculation. So this one you can use for geometry optimization for ligands, ligand conformations, and ligand poses. Mostly DFT functions, most of the DFT functions and basis set are present within FLAIR, and it is very easy to access and easy to use. With a few options using and tricks, you can run your quantum calculations. You can also generate QM electrostatic potential map and electron density map using this model. And also you can do a QM torsion profile for a selected low orbital bond. So if you want to rotate the bond around this and try to see the energetic, so it will show you the related energetics, and then accordingly you can choose which is the most favorable torsion angle for this. If you have very big molecules and DFT is becoming very expensive for running the optimization for the big molecules, you can use the semi-empirical method DF into XTB, which takes much lower time than DFT, but it gives you very reasonable results for the optimized structures. So you can use this for peptide molecules. The reason for version of FAIR has the capability of giving you the HOMO-LUMO orbital plot as well. So you can look on the HOMO-LUMO orbitals for a particular ligand and then decide on its reactivity. FAIR now has a very comprehensive ligand preparation method. So if you have a 2D structure of the ligand, which you may have downloaded from any drug discovery drug database, or maybe have drawn using the chemical or the tool which is presented in FAIR, you can then convert into 3D using this ligand prep module. You can recharge for pH 7. You can enumerate the chiral center if they are present, and you can also enumerate the number of tautomers if tautomers are possible there, and then you can pop this to 3D and minimize. So you convert it to a 3D structure and then minimize the structure based on a semi-empirical method. So this is a module which will help you to prepare your ligand, propionate it correctly. So already we have a very extensive module for preparing the protein, but now we have a very extensive module for ligand preparation as well if you have 2D structure and want to prepare your ligand before running any calculations. We have a module called fill templator for pharmacophore module. So there are some cases where you do not know the target structures of the ligand, but at least you have 2 or 3 ligands with known activity and 2 or 3 ligands from different chemical series which are known to be active ligands for a particular protein, but you do not have the target structure for it. Then how would you decide what will be the conformer for the ligand? Because you cannot run any docking calculation, you do not have any extra crystal structure for the ligand. So in that cases, this particular fill templater module is used. We generate a hypothesis out of how these ligands might bind, and then generate a conformer for it, which you can use as reference for aligning the histochemical properties. So this is an important module in cases where you do not have a target structure, but you have at least 2 or 3 known ligand for a particular protein. I have almost covered most of the ligand-based modules, though there are a lot more, but these are the main ones. Let me now speak about the structure-based method which FAIR has. FAIR has a pocket detection tool. So there are cases where you do not have extra crystal structure ligand, so you do not know that where the ligand might bind. So this is a very useful module for that. You can run this pocket detection calculation, and it will detect all the pockets, binding pockets that are present within the protein, and then it gives a druggability score. So based on the druggability score, you can choose a particular pocket where you want to dock your ligands. So even if you don't know where the binding site is, you can use this tool for finding out the binding site, and then binding pocket for running your docking calculation and generating grid for your docking calculation. So this can be also done in a molecular dynamics simulation where you observe the frequency of the pocket opening and pocket closing. So while running a dynamics calculation, there are cases where the pocket becomes smaller while going along the dynamics. So you would want to know that what would be the volume going along. So then this pocket frequency tool, it will observe the frequency of the opening and closing of the pocket, and then you can monitor the druggability of the pocket over the dynamics trajectory. We have a very useful water stability analysis tool. So there are cases where you have crystal water structures, crystal water present in the binding site, but you do not know that if the waters are happy or unhappy. So GIST is a tool which is molecular dynamics based and helps you to calculate the thermodynamics properties. So it calculates the del G negative and the del G positive, and also the enthalpy and the entropy for a particular water molecule, and then helps you to understand if the water is happy in the pocket. For example, here you can see this water has a green surface, that is del G negative surface, and hence it seems that this water is happy. However, this particular water here has a red surface attached to it, which has a del G positive value, which means that this water is unhappy here. So while designing the ligand, so this is a specific module in Spark as well. So So when designing a ligand, you would want to replace this water molecule and row the ligand in this direction. So if you want to row the ligand in this direction by replacing the water, it might create some turmoil and instability in the binding site, and it will make the ligand unstable and binding energy will decrease. If you replace this water molecule and you want to increase a functional group, put a functional group in such a way so that this hydrogen bond remains intact when this water is replaced, you might get a newly designed ligands which have a better binding energy, but you do not disturb the system because this water was not happy here, so you could replace it. So before designing your ligand, this is a very important step that this module will help you to do. What is called the GIST. The GIST is slightly computationally more expensive module because it runs a molecular dynamics of at least 20 nanosecond. But if you do not have that much time or computational resource, you can also run the 3D risk, which is an analytical method for determining the position and stability of water. So it gives you small dots, which are densities of water. And you can see the slightly green water, which means that this is more stable, and the red water means it's unstable. You can run a 3D regime calculation to understand that what are the water sites in the binding pocket and also understand the stability of water. Though this is computationally very less expensive than GIST, but this will gives you very reasonable understanding of where the water density lies and what is the thermodynamics of the water. Is it happy or unhappy here? We have a very easy to use MD calculation module where you can easily set up your calculation with few clicks, and then you can also analyze the results using few clicks. So you do not need to run any command line tool for running the dynamics or visualizing the analysis. You have an option of running it through command line, but you do not need to do it with code on call. So while running the molecular dynamics, what you can do is you can study the conformational changes of the protein that is happening in the dynamics run, and also assess the stability of the protein ligand complex. So let's say you have run docking for a large number of ligand and you have got very good docking energy, but then you want to see that if the ligand would be stable in a longer run in the pocket. So you can run a molecular dynamic simulation to see that if the ligand stays within or it goes out of the pocket. So there, because the force field used in molecular dynamics is much better than what we use for docking, the empirical scoring functions. So it will help you to understand if the ligand would be stable in the binding pocket. The force field that we use for small molecules is OpenFF. So we have a consortium with OpenFF, and all the development that happens in the OpenFF force field comes within FAIR. Other than that, we have the other force fields like AmberCAP and AmberCAP2. We also have a custom Gaussian force field, which is based on, one is based on machine learning and the other is based on UM calculations. So if you don't want to use this force field for the small molecules or the ligand, you can also generate your custom force field. There are all the solving models, accurate solving models included in the MD calculation, and we have a several advanced analysis tool like RMSD, RMSF. So you can use RMSD to understand the stability of the ligand in the pocket. You can also run a RMSF plot to see that which residue is flexible and moving more while doing the MD calculation. You can go, June.
Yeah, I got it.
Okay, thanks. Thanks. And then you can also look at the 2D RMSD plot and monitor the protein structure changes. You can also look at the contact. You can also look at the contact table to monitor the favorable ligand protein contact and interactions. So that would help you to also measure the distance with changes which is happening along the dynamics. So you can choose that which distance you want to check between the ligand and the protein residue, and it will give you a plot according to it how the distance has changed along the way. So it will help you to monitor that how the ligand movement has happened along the dynamics. We have the radius of gyration plot. that will help you to understand the structural changes, flexibility, and also the dynamics of the protein. These are all automated analysis which happens in a single click. But other than that, if you want to do some additional analysis, that is also can be done using the PyPlayer scripting. You can rather either write to us if you are having some problem doing any analysis using your Python scripting. Our team can help you provide PyPlayer script so that you can run those analysis as well. In the dynamics, we have also added something called GCNCNC. So this is an efficient sampling of the hydration pattern. So there are some cases where you do not have crystal waters. So the crystal structure doesn't have any water. You do not know where the water lies. In dynamics, you add water, but sometimes in dynamics, it is not able to add water to the hidden sites. So GCNCNC is a method which helps you sampling the hydration pattern better, and then it increases the hydration better and helps in predicting better in the simulation or better poses after you have run the MBA dynamics. So you can either put this GCNCNC on, or you can put it off as well if you have already crystal structure water and you know the hydration is correct. Um, so as I said, other than the force field which are present, you can also add custom parameters for the small molecules. You can either use the DFT, DF into XTB, which is a semi-empirical method. You can also use ANI2X, which is a machine learning based method for calculating the custom parameters. For modeling the loops, if you have any gap between the residues, if you have 15 to 20 gaps, you can download the spread database in your local system, and then you can model the loop. And then based on the different energetics of the loop or which one is favorable, you can choose the particular loop you want to keep. So this is possible only for 15 to 20 missing residues, but in FLAIR-V9, which is coming up in June, we would be having a full homology modeling module where you can do a homology modeling for a target structure where you do not have any crystal structure. We have our enhanced protein editing tool, which is where you can also grow a peptide. So if you give the sequence for a peptide, it will generate the peptide, and then you can build a peptide as a ligand, and also you can select if you want to build it as a beta shape or a alpha helix. This is a new editor that is present. It will help you to build your own peptides within FLAIR. And as you know that FLAIR FP is a independent module which doesn't come with FLAIR Pro Plus, but if some advanced user uh, who are ready to use a computationally more expensive method and more accurate method, they can use FLAIR FP. FLAIR FP within Crescent is also done in a very user-friendly way and in collaboration with Julian Michel in University of Edinburgh. So several open source tool and academically developed tool has been combined, and then with the expertise of Crescent's in-house scientists, they have made it very much user friendly in terms of the interface, so that anyone can run FEP calculation. So in this FEP calculation, what is done is you can calculate the relative binding energy of a conjugate series of ligands. So let's say you have 5 known ligands with known activity, but you have designed several other ligands which you want to know that if those ligands are better active than the ones which you have or lower active. So FEP helps you to calculate the relative binding energy of those ligand and helps you to understand that if your design ligand is better and how you can make it better, so that once you design the ligand, you run it with the FEP calculation, and you can understand that if it would have a better activity than the known ones or have a lower activity than the known ones. Though this FEP calculation is quite expensive and would need GPU servers to be present, otherwise it would be very slow. So you would need at least 10 GPU to run FFE at quite a good speed. It is used only for the advanced user. And then we have the Flare Python API where you can use Python snippet within Flare to create your own workflow, or you can automate a common task. Let's say you want to automate your task by adding 2 or 3 methods. Maybe you want to run docking, adding ABC, and then want to run some dynamics. But you do not want to do it stepwise, but you want to run a script which will run all the calculations at once. So you can create your own workflow using this PyFlare scripting, and also you can run a lot of analysis. You can integrate RDKit through PyFlare within Flare, and then you can use the RDKit functionality that are present. Other important function of PyFlare is a lot of people are there who do not want to run it from the GUI, or maybe you want to run a docking for huge number of gig and millions of gig, and so for graphical user interface it becomes very difficult and slow. So you can run it through command line directly without going into the graphical user interference. Or you want to run a dynamics, but you do not want to run through GUI. So every functionality which I have shown till now can be run in a command line basis as well. So you do not need to run through the GUI. You can run it through command line using this PyFlare tool. So this is all about what Flare has in very short. There are a lot of other functions which are present, which I didn't mention today. But while going along, as you explore more, you will get to know that what are the potential it has within. So that's all from my side. I would like to ask now that if there is any question or if you want to elaborate on any of the modules.
Dr. Dhruv?
Yes.
Actually, firstly, we don't know how to use this software. When I asked to perform any type of calculation, so how one can use the data. So though there are number of modules that we have, nicely but the main thing is that how one can use the software, how one can run this type of
Yes,
calculation.
Dr. Raj. Yes, Dr. Raj. So for that, that is what I said in the beginning, that for that we have training materials and recordings as well. So not only training materials, now we have recordings for each modules. So that will give you a step-by-step instructions how to use our software. So along with that, we will go a case study, which will example case study, which will help you to understand what that module is doing. So after this call, I would share those material with you. I think I have already shared, Tanya, right?
Yeah, one tutorial
Last
we have already
week.
seen.
Yes, two, ligand based and structure based. So for nano particle, which means that it's solid material, right? So generally for solid material, there are two things which can be done. If you want to do QM calculation, then generally plane wave DFT is done. So Flare is not a tool for doing plane wave DFT because it runs for drug molecules. But if you want to run dynamics, for example, if you want to run molecular dynamics for solid materials, then you can use our molecular dynamics tool for running any dynamics. But if you want to run something like plane wave DFT, something what I think VASP or CP2K kind of software does, so that Flare is not a software for that. Flare is a software for drug design. So
Basically, we are preparing the data matter and the nanoparticle size in order to enhance the activity, biological activity of this particular drug.
okay. So do you have a nano? Like you were saying that some nano
So
surface or nano. Do you
yes,
have the
if
structure for
we are
it?
taking to the say for example it's a nanoparticle and some metal based rock and we are going to form a structure in order to check actually whether it is going to increase or decrease or whatever the calculation on the metal
Okay. So the metal-based drug, of course, you can run within pair. You can run docking. So once you have formed that complex of nanomaterial and the drug, if you have the structure for it, so you would not be able to calculate the binding energy of the nano surface and the drug. Like the composite, you might not
जल्दी
be
चले
able. You
जाऊंगी हाँ
can do it,
अभी तो
but
एक नहीं
you can
चलाऊंगी
have to use the QM calculation
तो
method
से
where you
चलाऊंगी
form a structure and then you calculate
बस
the
वो
whole, and
किचन
then
में
you can separately calculate the energetics for the nanocomposite
बैठ
and the
जाओ
metal drug.
आप उसकी
But
वो
then
वो
again,
फेंक
if
दी
it's
नहीं
a solid surface, I would recommend that
है चेयर
using
फेंको
static DFT is good method to do that. Only plane wave TFT can give the energetics for the composite. But if you have the structure for the composite, then you want to do any docking calculation with the protein binding site, then you would be able to do that within pair.
so player is meant only for docking with the protein or we can go for say DNA.
No, no, you can do for DNA as well.
Okay. So the procedure will be same for that also.
Yes, the procedure will remain same.
So say I have used autolog phosphate also. So
Mhm,
most of the mechanisms are not there in the library.
mhm.
So the way my teachers say that all the atoms in the library are there. But sometimes say we are using say certain other components or maybe the amylase is there or some other kind of processes are there. And say some of the metals are not there in the library. So
Okay. So generally, Dr. Raj, most of the metals are included within the paired force field, what we are using for OpenFF or Amber or GAF or GAF2. You can also, if the metal is present within the ligand. So as you are seeing, ligand metal-based drugs, so it will present within the ligand. So you can use the custom force field for building the force field. So generally, what happens is the force field doesn't have the parameters for that particular metal. So you can generate it. What I can do is I can share a list of the metals and whatever is there uh, with you, so that you can check that if that suffices you need.
any other question? Dr. Jagannath?
Uh, a bit low, voice is a bit low.
Dr. Jagannath, your audio not clear.
थोड़ी बहुत तो है थोड़ी कम है
वॉल्यूम
आवाज
थोड़ा प्लीज वॉल्यूम
Yeah, Dr. Jagannath, you can speak, but the voice is very low actually. Let me see if I can hear you. Cannot hear you. You can put it in the chat.
Yeah.
No, no, you can put it in the chat now so that I can clarify. Okay. Okay. Then you can send the email to me.
कुछ नहीं बस ऐसे बैठा हूँ नहीं वो उसका लैपटॉप यूज कर रहा है
Okay, thank you, Dr. Boily, for your presentation. Am I audible?
Yes.
Yeah, you're audible.
Yeah, again. Okay, so thank you very much for your presentation. Nice presentation. So I have, I think this is second time I am hearing this thing. Okay, every time I learn something new from you. So just so I do not have any query in general. So it seems to be very interesting to use this software package with this player, and I hope that you people will tend to because many of our students who are new and for the first time they will be doing this kind of things, na? So they need a little bit more assistance or support from your side, little bit. So I hope that you should extend that thing whenever they need it for their work.
Yeah, of course, we will do that. So I have shared some training materials which you can download. So what I
Okay.
planned is those are quite detailed, and those are recording as well. So generally, before what we used to do live trainings, but because we have worked very hard to do recordings, so that they can
Recording.
do it in their own pace, so that
Yes,
they
yes.
can learn it
Okay.
in their own pace. So we would do a
So
Q&A
please
session
share those.
also.
Yes, please share those recordings and
I
those
have
kind of.
shared the modules
Yeah.
last week, so everything is
Okay,
within
okay,
this. I
okay,
have
okay,
shared the modules last week. Okay, everything is
okay,
within
okay.
that. You can download it, or if any problem with downloading, please let me know. It shouldn't be, but please let me know if any problem with downloading. After they
Okay,
use a little bit, we can do a Q&A session. Sorry. So if whatever question they have, I will try to answer it there or explain there. After that, also, if any training is required, I will do the live sessions.
yeah, yeah.
And they can write to support anytime they want. So support is very active. They will answer within half a day. So they can write to the email support @freshers.com. Kanaya will also share with you. So they can write to support at any point of time they want.
Okay, okay, okay. That's very nice. Okay. So students, do you have any thing to ask? Any query? You are the users basically.
No, sir. We'll try to run these
Yeah, yeah, yeah.
tutorial files, then we'll
Yes, I think that's the best option. First, try to use that thing, and now next time when you really use that thing, you will face some problem that can be resolved by your experts. Okay, ma'am. This session concludes.
Thank you, everyone. Thank you for joining the call.
Thank you,
Thank
Boily. Thank you for conducting it
thank you,
so
ma'am.
effortlessly.
Thank you. Goodbye. Kanaya.
Thank you, Dr. Raj.
thanks, Dr.